Hei! Velkommen til GEO-Onsdag her ved Universitetet i Oslo og ved Matematisk-naturvitenskapelig fakultets bibliotek. Og dette er et veldig fint evenement vi har en gang i måneden. Dessverre i dag igjen uten publikum på grunn av disse rare koronatidene. Dette her blir vår siste GEO-Onsdag i denne sesongen, så vi vil ha flere, selvsagt etter sommerpausen, sånn fra september. Og i dag har jeg den store gleden til å introdusere professor Luca Menegon. Var det riktig? Luca Menegon. Luca, han er født i Bolzano i Italia, italiensk, og han har tatt sin master og sin PhD på Padua Universitetet i Italia. Og han er strukturgeolog, jobber mye med tektonikk, strukturgeologi, mineralogi, fluider i bakken, og vi vil sikkert høre mye mer om dette senere. Luca er internasjonal person, han dro til Storbritannia, til Plymouth, og var der en del år, og var faktisk også i Tromsø en del år, så han er halvnorsk nå snart. Siden 2018 har han vært ansatt Siden 2018 har han vært ansatt her ved Universitetet i Oslo, ved PGP, altså GeoPGP, Physics of Geological Processes, og også Njord Center, som er et senter mellom geofag og fysikk, og som jobber veldig mye i skjæringspunktet mellom disse to fagene. I dag skal Luca gi en presentasjon som har titlen «Hunting for fossil earthquakes in the Norwegian rocks». Vi har normalt ikke så veldig mange jordskjelv i Norge, så Luca har funnet gamle jordskjelv, og det får vi høre om nå. Vær så god.
Tusen takk. Tusen takk, Bert. So thank you very much. It's my pleasure to be here this afternoon. Thank you to the virtual audience at home or in your offices. I hope I will make you more curious about what fossil earthquakes are, a bit more curious also about the spectacular opportunities that Norwegian geology provides us with investigations of fossil earthquakes. I will give about half an hour of presentation about the science that motivates this research, but I also like to introduce my colleague in Plymouth, Heidi Morstang. She is associate professor in photography, and Heidi has produced a documentary about our fieldwork in Lofoten a few years ago. So we interacted with a documentary and with a filmmaking process, and I hope you will become a bit more curious about that towards the end of my presentation. Okay, so I'd like to convince you today that we can put our finger on a fossil earthquake, and we can take a sample of rocks that represents fossil earthquakes, and we can study them in the laboratory to understand more about how earthquakes work. Then I also like to convince you that here in Norway we have the Himalayas in our backyard, mostly in a couple of localities along the western coast. And then I like to dive a little bit more into how earthquakes transform the Earth's continental crust through a variety of mechanisms. And then I will move towards the documentary that I have just mentioned that Heidi has produced, which is nicely summarized with the statement that every earthquake starts in the size of a grain. Okay, what is an earthquake, first of all? Well, an earthquake is caused by the build-up of stress, of tectonic stresses on rocks, which at some point exceeds the strength of rocks and the friction in those rocks. And then when this happens, there is a sudden slip on a fault. This animation hopefully will show you what I mean now. So this is a plan view of what a fault might look like. You see an example of the San Andreas fault on the right-hand side of the screen. So the earthquake happens because there is a build-up, a progressive build-up of stress along the fault, and when this stress is released suddenly, the earthquake occurs by a sudden slip on a fault. So earthquakes are a manifestation of plate tectonics. So they predominantly occur at plate boundaries. We see a map here of the global distribution of earthquakes and volcanoes as well. And the earthquakes are predominantly located at plate boundaries. For example, the mid-ocean ridge, which is a divergent plate boundaries that separates two plates on both sides of the Atlantic Ocean, but also on convergent plate boundaries like the subduction zones here in South America, but also along transform plate boundaries like the very famous San Andreas Fault. However, although they are predominantly located at plate boundaries, they also occur in the interior of continents. We have a few examples in the United States, here in Australia, or in Central Asia. And these can also be quite devastating, like those that happen in subduction zones. So this map of global distribution of earthquakes is mirrored in the map of the global seismic hazard, which in the color code, in the color scheme here, shows very low seismic hazard in white and very high seismic hazard in red. So the red zones overlap quite tightly with the plate boundaries on land, so on areas with a high number of people living nearby. So if we zoom in a little bit into Europe, we have this map here now, which represents the European seismic hazard map. And most of the seismic hazard is located in the south of Europe, in Turkey here. This is the fault called the North Anatolian Fault. This is called the Eastern Anatolian Fault. These faults are located at the boundary of the Anatolian plate, essentially Turkey and adjacent regions. And these faults are particularly dangerous, not only because they are active, but also because a big city like Istanbul lies here, and therefore the earthquake hazard can be particularly high there. Let me open the laser pointer. Okay, North Anatolian Fault and East Anatolian Fault here. Italy is also quite dangerous when it comes to seismic hazard, so I deliberately escaped from Italy and I moved to Tromsø, where there is much less seismic hazard, and then I drifted towards southern England and Plymouth, which is also very low seismic hazard. And I'm now here back in Norway, in Oslo, where the seismic hazard is also fairly low. But if you want to know more about seismic hazard in Norway, I refer you to the NORSAR, which is the Norwegian Institute for Seismology and monitoring of earthquake activities. So here we have an animation that shows the earthquake distribution in the last 10 years, if I remember correctly. And they mostly occur in the northern part of the Atlantic, in proximity of the mid-ocean ridge, but in Norway earthquakes are more rare. They do occur though, but they are more rare. The last fairly relevant earthquake that occurred in Oslo was in 1904, if I remember correctly from what I have read in the recent days, and I think it was a magnitude 4. That means that another one could happen in the future, but more research is needed in this field. What about the depth? So where does the earthquake rupture nucleate in the Earth crust? So earthquakes are predominantly a shallow phenomenon, as we can see on this map here, where the size of the symbols represents the magnitude of the earthquake, so the strength, the intensity of the earthquake, whereas the color gives us an idea of the depth. So we have a dominance of red and orange color in this map here, which denote earthquakes that happen at depth within 50 kilometers, let's say. However, fairly deep earthquakes down to hundreds of kilometers depth into the earth do occur. They do occur in what we call subduction zones, when one plate is going underneath another plate to large depth. These are a special category of earthquakes that I'm not going to deal with particularly today, but be aware that these are also an important manifestation of geodynamic processes. So if we stay tuned on the relatively shallow earthquakes, which are the majority, within the first 50 kilometers of depth, we can also identify another subdivision. So we can identify what we call the seismogenic zone in the Earth crust. So within these 50 kilometers of depth, most of the earthquake occur between 5 and let's say 15, 20 kilometers. This is a recent compilation of earthquake frequency from a few areas that are particularly prone to earthquake activity. So Tibet, Iran, the Aegean, in the Mediterranean, California, and Tian Shan. And the majority of earthquakes in this area occur at about 10 to 15 kilometers. So that's where the Earth crust is more prone to generate earthquakes. Deeper earthquakes also occur, and these are particularly important for what I want to say today, because most of the fossil earthquakes that we find in the Norwegian rocks are representative of this category of earthquakes down here. The earthquake deformation is also cyclical, right? So we have a diagram here that shows on the y-axis the strain, so the amount of energy that rocks are accumulating in the course of the geological history, versus time. And you see there is a sort of a repeatable cycle here of situation and events. And the geologists and geophysicists have given specific names to different branches of this cycle. The interseismic period of the earthquake cycle is the period during which the strain is accumulated in the rock. So the stress and strain, the rocks are loading, okay? They are building up all the stress and strain, and it is then subsequently released through the earthquake activity. And when the earthquake happens, we have a sudden co-seismic slip. So the slip that happens during the generation of the earthquake. This co-seismic slip, however, generates perturbations and stress readjustments in the adjacent rocks, and these stress readjustments denote or identify what we call the immediate post-seismic creep. When the post-seismic creep is over, when the region has gone back to the, let's say, regular, normal stress state, then the next interseismic stage begins. If you want to look at these things in a nice block diagrams here, so the interseismic period is the period during which the fault is loading, okay, is accumulating stress and strain, and it lasts for hundreds or thousands of years. It's a long-lasting process. The co-seismic slip, that's the earthquake itself, is very fast, as we all know. So it's a matter of seconds or minutes, and that's where the fault slips and then dissipates energy through a variety of mechanisms, most notably shaking when it comes to how we feel the earthquakes. Then immediately after the main shock of the earthquake, we have this local adjustment of stress in the rocks, which identify the post-seismic deformation stage, which is shorter than the interseismic in duration, but is longer than the co-seismic. We're talking about days to decades. Okay, how does this mechanism of loading strain and stress and releasing of energy works? Well, if we look at this diagram here, this diagram shows us what happens to a fault and to a fault slip with depth. So the interseismic slip is when the fault is loading, is building up the stored energy that is going to be released afterwards. At depth, typically this interseismic slip manifests itself in the form of what we call ductile deformation. So the rocks are capable, in the deep roots of a seismic faults, the rocks are capable of flowing, like if they were chewing gum, essentially, right? So they're creeping and flowing with depth in a deformation style that we call ductile, and which is associated with aseismic viscous creep. So the rock are flowing like a viscous fluid, but they are still solid state. The rocks that are representative of this category of deformation are called mylonites on Earth, and this is an example. So in this black layer is a ductile shear zone where we find a mylonite. This white layer here is what we call a marker that gives us an idea of the amount of deformation has been accommodated during this viscous flow. You can see that this marker is continuous across the shear zone. Okay, we don't have fracturing here, we don't have a loss of cohesion. We have the accumulation of offset of the marker through viscous flow. And this viscous flow in the deep roots of the fault is loading the shallower part of the fault, and when the upper part of the fault cannot keep up with the viscous flow at depth, it snaps and it forms an earthquake, which is here denoted as co-seismic slip. And the rocks that we find representative of these mechanisms are rocks that have been deformed in a brittle way. They have been fractured, they have lost their cohesion, they have been fragmented, they have been intensely affected by fracturing and frictional sliding. So essentially in this simple model, the loading starts from below, from the deep roots of a fault, and then loads and charges the upper part of a fault, which snaps when the energy is too high, the stored stress is too high. What happens here in the post-seismic slip is a bit more difficult to understand. So while we have a relatively good understanding of the manifestation of interseismic slip and co-seismic slip in the geological record, and these two images are good examples, we don't know much about this very short-lived post-seismic deformation, which is an emerging field of research in earth sciences. Okay, what about the magnitude, the strength of an earthquake? So how much energy it can release? Here we see a diagram where in the central part here we have the amount of earthquakes in 1 year that occur globally for a given magnitude. The magnitude is a number that measures the energy released in an earthquake. And every unit of difference defines an earthquake that is 32 times more energetic than the one below it. Okay, so we are talking about really large differences in energy here. So to give you an example, magnitude 3 is representative of the same energy released by a lightning bolt. Whereas if we go higher up, we have much less and less earthquakes of high magnitude. Luckily, we have less than magnitude 9 earthquake per year. These are incredibly destructive, and the relatively recent earthquake in Japan, in Tohoku 2011, is one of the examples of these catastrophic events. And because I was mentioning Tohoku, I report here a quote from an article published in Physics Today shortly after the earthquake that gives us an idea of how intense and catastrophic the release of energy has been at that time during the earthquake. So the energy released during the Tohoku earthquake was equivalent to 100 megaton explosion. So we're talking about massive energies at play here. But what is actually the concept of energy of an earthquake? Well, the energy of the earthquake is essentially the stored stress that rocks have built up in the course of the geological history, and which are released during the earthquake itself in the form of different dissipation mechanisms. These are the typical manifestation of types of energy released during an earthquake that we might be familiar with. So the radiated energy is what happens when the seismic waves propagate through rocks and cause the high damage to cities and infrastructures. So they are associated with the shaking, right? So, and this is quite a relatively small slice of the cake here. So although earthquakes can be quite catastrophic, the amount of energy that is released in the form of radiated energy and shaking is quite low, and is enormously lower compared to the energy that is released in the form of heat because of the friction between rocks, right? So if you slide your hands, you generate heat. Luckily, you don't generate an earthquake, you don't melt your hands, but you do generate heat. And the heat is by far the largest amount of energy released during an earthquake. There is another fraction of type of energy that is also being considered, where we called about dissipation of energy of an earthquake, which is the energy necessary to break the rocks, to create new fractures and new surfaces during the fragmentation process. So heat is the most important type of dissipation process of the stored energy of faults. And this is particularly important for what I want to discuss today, because heat is capable of melting rocks. And when the heat at play is really, really high, specific rock types can form that are called pseudotachylytes. These rocks were introduced in 1916 by Njord and described as an inclusion-rich black rock with a glassy or cryptocrystalline matrix that resembles the basaltic glass or a tachylite. But it's not a basaltic glass. These rocks are not volcanic in origin. Okay, their origin relies on friction. They are the result of frictional melting of the rocks. Hence, they are pseudo-tachylite and not tachylite. In this diagram here, we see the type locality of Pseudotachylytes, which is in the Weatherford impact structure in South Africa. These black rocks here are the result of a sudden melting during shock deformation of the granite, the host rock here, following an impact from an asteroid or a rock coming from the space. So these are pseudotachylites that result from shock deformation due to impacts. But we also have the example of tectonic pseudotachylites, which are found along faults, along seismic faults. These tectonic pseudotachylites, we see an example here, are solidified frictional melt produced during a seismic slip. So when the rocks were sliding a seismic rate of at least 1 meter per second. Therefore, when we see these rocks in association with faults in the field, we can put our finger onto a fossil earthquake. The pseudotachylite has a specific structure. This is the main slip zone where this fault block has been sliding past this fault block here. And these are what we call injection veins. So the melt generated by the friction during the high velocity sliding has been extruded wanted to escape from the sliding surface and has been extruded towards the host rock here. So whenever we see these rocks in the field, of course, they are very, very important because they give us the opportunity to dive into the secrets of an earthquake. So what type of information can we derive from these rocks in the field? This is an example of a fault in the Italian Alps, the Gole Larghe fault zone. And the Gole Larghe fault zone is decorated by pseudotachylites, which have injection veins. And this study reports that the injection veins are asymmetrical. They are much more numerous and abundant in the southern block of the fault. From this very accurate and detailed field observation, the work of Di Toro and co-authors has demonstrated that this field observation can be used to derive the directivity of the earthquake rupture, to understand where the rupture has been traveling, in which direction the rupture has been traveling. So this modeling, which is informed and based on detailed field observation of the Gole Larghe pseudotachylite, is consistent with an earthquake rupture that propagated from the west to the east along the Gole Larghe fault, and is consistent with the southern block experiencing more tension, so more tendency to open gaps that were filled by the injection vein of the pseudotachylite. So from careful field observation, we can understand more about how rocks break during an earthquake. Likewise, we can take samples of pseudotachylite, make very thin slides of rocks and look at them in the microscope and find a plethora of what we call microstructure that are indicative of frictional melting and rapid quenching from the melt, like what we call microlites down here, which are typical of pseudotachylites and indicate rapid quenching from a melt, as well as chilled margin. So this margin of the pseudotachylite has been quenching very rapidly because it was in contact with the host rock. When I say quenching, I mean that the frictional melt produced during seismic slip can be up to 1500 degrees in temperature. But the host rock that is hosting the earthquake might be just a couple of hundreds of degrees. So there is a delta T that is dramatic across this boundary. That's why the frictional melt here quenches instantaneously. So it's very important whenever we want to understand more about these rocks to dive really into the microstructure and into the tiny grain scale details. We can do that here in Oslo with what we call electron microscopy techniques. This is our electron microscopy lab at the Department of Geosciences, which can generate a variety of images and a variety of maps that provide plenty of information about the morphology of the tiny little grains subjected to rock deformation, the grain size, the internal amount of deformation, the bending of the crystal lattice, as well as the composition here. So these are fantastic tools for us to dive into the secrets of rock deformation and earthquakes. With this approach, another study here has demonstrated that the pseudotachylite of the Gole Larghe, the one that I have introduced earlier, developed during a process that dissipated energy to a large extent through heat. So although the energy balance of the earthquake is largely derived from seismological studies, from indirect studies, looking at rocks can confirm what indirect studies have quantitatively estimated by direct observations. In this study, the authors have measured how many fractures there were in these pseudotachylytes and in the adjacent rocks, and have concluded that the fracture energy is irrelevant compared to the contribution of dissipated heat in the process of frictional sliding and earthquake generation. Okay, we can also reproduce this frictional sliding and frictional melting in the laboratory using an apparatus called Shiva's low to high velocity apparatus, which is installed in the laboratories of the National Institute of Geophysics and Volcanology in Rome and led by Professor Giulio Di Toro from the University of Padova. And this is an earthquake simulator, one of the probably the most powerful earthquake simulator. It is capable of shearing rocks and at sliding velocity up to 9 meters per second, so simulating what happens when two rocks slides past each other during an earthquake. I'll show you a video now. This video will show us
Ok, puoi andare per me.
Pseudotachylytes in the laboratory. Okay, the rocks are sliding at seismic velocities and
Basta. Stop, stavo fondendo tutto.
I go back to the presentation. Okay. Okay, now I want to show you why fossil earthquakes are important in Norwegian rocks. So with this introduction about pseudotachylite, what can we understand about earthquakes looking at Norwegian rocks? We have two main areas in Norway that are particularly valuable as natural laboratories for fossil earthquakes. One is Lofoten and one is the Bergen Arcs and the Western Ice region near Bergen. So Norwegian fossil earthquakes are very special. They are special because they formed relatively deep in the crust. They formed where the crust is expected to flow viscously instead of breaking and generating earthquakes. So they form, this is a metamorphic fascist chart, they form down here at 30 to even 70 kilometers depth. So those belong to that category of earthquakes that are below the classic seismogenic zones. And these are particularly challenging to explain. So lower crustal earthquakes are less common than earthquakes that occur in the top, let's say, 15 kilometers of the crust, but they do exist and are particularly difficult to explain. They do exist, for example, also in relation to the Gorka earthquakes that happened in 2015 in Nepal. So this cluster of earthquakes here defines the main shock and the main seismicity associated with the Gorka earthquake cycle, which happened at about 10 to 15 kilometers depth. But all this cluster of aftershocks here, which are within the red ellipse, they are at depth of about 25 kilometers. And that's very difficult. These are more difficult to explain because at those depths, the rocks in the Himalaya should flow viscously. So the idea is that perhaps the Norwegian fossil earthquakes are analog or are similar to what happened to the Gorka earthquakes or similar to aftershocks of the Gorka earthquakes. Explaining these lower crustal earthquakes is difficult because there are challenges here. Because seismic fracturing at depth requires very high stresses. So if we want to generate a fracture at 30 kilometers deep, we need really to apply a large stress. Otherwise, the confinement prevents fracturing from occurring. And these rocks at depth at the same time cannot build up much stress because they are expected to flow plastically to generate mylonites. So how can we solve this conundrum? Well, let's skip this one. Well, the idea here is that rocks at depth can store a lot of energy if there is no water. Okay, so the viscous flow of rocks at about 30 kilometers depth is facilitated by the presence of tiny amounts of water in the crystal lattice of the mineral grains that facilitates viscous flow. Otherwise, they would really be prone to cracking, because lack of fluid increases the strength of the rocks. So if the rocks are dry, then they can sustain more stress and they can generate earthquakes at depth. And we will see that this is exactly the case for Norway. I move to this one here. So about 30% of earthquakes of magnitude higher than 5 nucleates in the lower crust at depth higher than 25 kilometers. These are typically found in areas that we call the Precambrian shields, Africa, India, and Mongolia, Baikal. Precambrian shields are rocks that are very old. They're very old, they have been dehydrated. All the water has been taken away from the crystal lattice, and therefore dry rocks can build up a much higher stress and can release earthquakes also at depth where they are expected to flow plastically. India is an example. We see earthquakes that are quite deep in India, here, up down to 80 kilometers. This is the Bhuj 2001 Bhuj earthquake in India, which has been interpreted to reflect the presence of what we call granulites in the Indian lower crust. Granulites are rocks that are dry. They are dry. These rocks come from the Jotun nappe in the Bergenarks, are rocks, granulites consisting of plagioclase, pyroxene, and garnet. There is no water there. So these provide us with a snapshot to understand deep crustal earthquakes, because we have the correct rocks here in Norway. Our Himalayas, for example, is in Holsnøy in the Bergenarks, where in 2019 a group of scientists from all over the world met to discuss earthquakes in the lower crust. Or in Lofoten, where we are conducting field work quite regularly at the Department of Geosciences. Lofoten and the Bergenarks give us a window into processes that happen at 30 to 50 kilometers depth, which is far deeper than the deepest hole has been drilled in the continents, which is the Kola super deep borehole that reached about 12 kilometers depth. Okay, in the Bergenarks we see pseudotachylytes, so that's the pseudotachylite vein, which separates two different rocks, granulites from eclogite. This is the pseudotachylite fault that offset this layering here. So this is a fossil earthquake that happened in the lower crust of the Bergenarks. The research on lower crustal earthquakes has really blossomed in Oslo. So this is the enlightening work by Håkon Austrheim and co-workers, and it's something that continues to keep us very busy and very much into this topic these days. So when an earthquake occurs, it creates fracturing and enables fluid to infiltrate into the rocks, and these fluids are capable of weakening the rocks that were otherwise dry and strong. And if this weakening happens, the rocks can start to flow plastically to form ductile shear zones. So the earthquakes are agents of transformation of the continental crust, in this case from dry, stiff, strong rocks that do not want to deform to weaker, hydrated rocks which are more happy to flow viscously. Okay, it also tells us that earthquakes is a fundamental ingredient to trigger metamorphism, so the change in mineralogy of rocks, because metamorphism require fluids, but if rocks are dry, how can we infiltrate fluids? Through earthquakes, through fracturing, fragmentation, and fluid infiltration that facilitates mineral reactions. This has been proposed for the Bergenarks, a model where, again, the link between Western Norway and Himalaya has been proposed. So the pseudotachylites in the Bergenarks are, in this model, equivalent to the aftershocks that happened in the Bhuj earthquake or in the Gorka earthquakes. So these pseudotachylites are the result of stress propagation downwards into the lower crust from shallow crustal earthquakes with the infiltration of fluids and hydration and mineral reactions. So earthquakes are fundamental agents of transformation of the earth crust. Lofoten, last 5 minutes of our journey through Norwegian rocks. Lofoten are also another great natural laboratory for lower crustal earthquakes, in particular the Njord ridge in the island of Flakstadøy, where we see from aerial photograph and from the topography a lot of lineaments, and all these lineaments are faults decorated by pseudotachylites and mylonites, faults that tell us that the entire earthquake cycle is preserved in nature for us to take samples and learn more. So all those structures indicated by arrows are pseudotachylites and shear zones, of which we see an example here. Pseudotachylite is this one here, and these are other pseudotachylite here. So when the earthquake occurred, fluids infiltrated the fault and made it weak and capable of flowing viscously to create a mylonite. And if we zoom in into this mylonite at a grain scale with a microscope, we would see a mineral that is called quartz that is has crystallized in these relatively fine, small grains. We're talking about 10 micrometers here. So the size of these tiny, small grains depends on the stress that was active during the viscous creep, during the viscous flow through this relationship on the right-hand side. In short, small size of quartz means high stresses and fast creep rate. In our opinion, these rocks here are the manifestation of this enigmatic post-seismic creep or post-seismic slip, where after the co-seismic slip that generates the earthquakes and the pseudotachylites infiltrated by fluids could continue to move a little more at fast creep rates to accommodate what we call the viscous stress relaxation around the fault. Okay, so this is something that we are quite keen to propose as a novel result. Okay, and in addition to that, these shear zones here, these ductile shear zones, these mylonites, are loading all the stiff blocks of granulites adjacent to them, and this loading generates new earthquakes which manifest themselves in the form of new pseudotachylite veins here. So if we measure the thickness of these pseudotachylites, if we measure the offset along the pseudotachylites, if we measure how much melt there is, we can try to derive what we call earthquake source parameters. For example, the magnitude of the earthquakes associated with those tiny little pseudotachylites, as well as the stress drop, so how much stress has been released during the earthquakes. And we see that this stress drop is very high in the case of the Lofoten pseudotachylites, and we think that this is very high because these rocks were sitting at depth, they were very strong, and they had a lot of energy to accumulate. That concludes the science part. I'm going to introduce Heidi Morstang and her film about pseudotachylite. Heidi is an associate professor of photography. Unfortunately, she cannot be with us today. I believe she is in the virtual audience, but she was very kind to leave a video for us. I encourage you to visit her outstanding portfolio of documentaries in her website here. We will also post it on the website of the University of Njord and of the initiative today. And Heidi left a video for us where she introduces the film. And the video, I believe, is ready to go. Thank you.
Hi, I'm Heidi Morstang. I'm a filmmaker and photographer and an associate professor in photography at University of Plymouth in the UK. I work with documentary film and photography, often on projects that are part of interdisciplinary research projects, and I'm particularly interested in landscape and how we intervene with it in order to seek an understanding of our environment. Today I will talk a little bit about the film Pseudotachylytes seen from my perspective as a filmmaker. I will also show the beginning of the film as a talk, although the film will be playing without sound during this presentation. So this is to give you a little taster of the film, so you can return to this in your own time. So I'm going to share the screen now so you can see a bit of the film. I was invited into Luca Menegon's project in 2017 with the opportunity to make a film about a team of geoscientists going to the Lofoten Islands. The film is intended to contribute to an understanding of how field scientists work and why physical field work is crucial to understanding the significance of visual interpretation. The starting point for making the film stems from an explanation by one of the geoscientists about how earthquake starts. He said, "Every earthquake starts in the size of a grain." I was immediately intrigued to think of really large, devastating natural events starting as tiny. And as a filmmaker, I interpreted it as, how do we connect microcosm and macrocosm on a conceptual level through observational documentary film? Why does landscape matter, and how can film contribute to an insight of our environment and of deep time? Pseudotachylyte foregrounds aspects of methods of scientific knowledge production and research that are not generally accessible outside of the scientific communities they concern. A key part of its originality lies in its focus on what is overlooked in the interplay between fieldwork and laboratory practices. In part, the film draws attention to the aesthetics of these methods, its visual richness and humanism. The portrait of a method is timely given the increasing prevalence of digital and remote science methodologies, and at the same time bridges the artistic landscape genre with the scientific practice of fieldwork. The film unravels how scientific thought processes are communicated and contributes to knowledge of how scientists make decisions, and consequently how these decisions define geological narratives. Its originality lies in its focus on what is overlooked in the interplay between fieldwork in landscape as a natural laboratory and laboratory practices. The articulation of cinematic and audio expression shift attention from verbal narrative to key importance of tactile and spatial understanding of geology as landscape. You will notice I use the term observational documentary film, and as this is a specific method of filmmaking that you can see in the film. You will see that there are no verbal explanations by the geoscientists talking directly to the camera. In observational documentaries, we have the opportunity to observe and take part in an event without being explained the narrative. We can watch and make up our own minds and be allowed to speculate and imagine. And this method gives no direct answers, but we have to figure out things by observation. And I'm fascinated by how scientists work and their thinking processes. For this film, I was also interested in discovering how we understand the connections between distant history and the future of earthquakes through landscape. I wanted to portray the inquisitive minds of geologists in order to communicate how one can decipher and interpret geological events of deep time, and how they try to understand the stories concealed in the layers underneath. So we filmed the fieldwork at the Njord plateau, the natural laboratory itself, during the summer of 2017, and in the electron microscopy center in the autumn. I wanted to show how they undertake those investigations and how they interact with landscape they are researching. And this is a relationship that most people won't get to see, but I think unlocking that connection between people and place is a key element of understanding research of this nature. I constructed the film as a quest, or perhaps as a kind of a never-ending detective story. It is driven by the geoscientist's curiosity and stamina to explore this one mountain plateau in the Arctic. In the film, you will notice how the sound changes at some points. I try to focus on the inner space, the mind or thought processes of the geoscientists when they explore the rocks. I also try to portray that doing fieldwork takes time, And the slowness in the film is an important aspect to get a sense of time and explanation of the work. And the underlying question in the film is, how do we understand and define history? I'm interested in how we intervene in landscape in order to advance knowledge. How does fieldwork look like? And what are the thinking processes involved in it? So, in the film, what intrigues me is, why do geoscientists pick up exactly that rock and not the one to the left or to the right? Why is a certain tiny sample selected for microscopic work? Does that selecting provide the accurate narrative, or would another rock offer a slightly different story? This is more of a philosophical question, and my interest in seeing how decisions are made and if intuitive approaches are part of the fieldwork and research processes that may have similarities to artistic processes. So, the film is 55 minutes, and I hope you will enjoy seeing it. Also with sound when you can watch the entire film. So, thank you for your time.
Okay, so thank you very much for your attention today. I hope you're all more curious about fossil earthquakes, Norwegian geology, and about the collaboration between science and art to make nice films and documentaries like the one that Heidi has made. Thank you, and have a good rest of the day.